So to design the hash function, the first hash function that we can think about is the modular-based hash functions. What's the modular-based hash function is that we divide the number key, numeric key, with a number, and the number, this number is going to often to be the size of the hash table. So that we can utilize if this hash table size is n, it's always going to result in 0 to n minus 1. And actually, if we add plus 1 here, then it's going to be 1 to n, right? And actually that maps to the size of the hash table. All the keys are going to be mapped to the hash table, right? So that's actually great because that the range is right, the index range is correct, and every key is going to be mapped. So it's going to be a perfect, which function? Yeah, surjective function. Because the key can be very big numbers. And there can be collisions. So it's going to be a good surjective function. So we take the remainder as an array index. For example, index is equal to key modular size. Write this. And if you have this table size and you have this ID, then this is going to be the index, right? Having said that, let's imagine we just change these numbers, but still have the same remainder. In that case, we have a collision between the two index. Why is this often used? Because it has a good variable range. Because it has a good variable range here. And appears to be uniform. If the key is has a good, nice distribution, and this remainder is also going to be the uniform. But the key is not going to be the uniform, so it's not going to be uniform. So in the real world, it's not, but it appears to be. Still a good surjective function, right? However, there is some problem of the modular-based operation. So people utilize different hash functions. For example, people utilize square-based hash function, or mid-square hash function is being called. The problem of the modular operation is that it underutilized available information. And for example, quotient is not used in Korean MOOC. For example, if we go back to one slide before, we are dividing 50,000. Means that we only actually interested in these 5 numbers. We only interested in these 5 numbers. We are not using these upper values. Totally not. Only remainder is concerned with these lower 5 digits. So this is the underutilization of the number system, ID system. So to maximize the utility, actually what we are going to utilize is the mid-scale values. Mid-scale values defined like this. For example, we have ID as 1, 2, 3, and 1, 2, 3. And if we multiply it, we have 3, 6, 9, 2, 4, 6, 1, 2, 3, and we all sum up, and we have these values. To create this 1, 1, actually the chance can be, it can be 1 or 2. It's being determined by this 1 value and 1 value and the coming values from the lower digits. But it's very limited selection, so it's much likely it can be decided by the upper values, and the variable changes just 1 by 1. And furthermore, this 9 values, 9 digits, is only being determined by this 3. value 3 here, so that it can be 9. So it's an underutilization of information, of the ID information, if we just utilize 1 or 9. On the other hand, the mid values for 512, actually to determine this 512, this mid term, these are all calculated by utilizing 1 and 2 and 3 fully. Without the information 1 or 2 or 3 values, we cannot calculate this 512. If we want to calculate 9, we don't want to know, we only need to know the last digit is being 3, so that we can find out 9. However, by knowing only 3 or only 1 or only 2, can we calculate 5, 1, 2 here? No. The mid-scale values requires the full information of the ID number system. First, scale the key values. Second, take the n digits in the middle. Third, apply the selected digits to the modulo operation. Because these numbers actually has the full information of the ID system, so that after taking these mid-scale values, then we go to the modulo operation. In that case, we can utilize the whole ID system information in the modulo operation hash functions. For example, if we have a key of 1, 2, 3 and table size of 100 and mid-scale values that we want to take digit is 3, these m values. In the case F123 is mid-scale value of 1, 2, 3 and modulo 100, and it's going to be 512, and modulo 100, and it's going to be 12. Still utilizing the modulo operation at the end. Why is that? Because it's about the range. We have a determined hash table size, and our index always be matched up by that size. And actually, modulo operation is the best method to keep that range intact. Okay, so only affected by the first digit, only affected by the last digit, and first digit plus the lower digit values, but it's pretty much defined by the first digit, and it's the variable change is +1, like that. And finally, the digit analysis based hash functions. That's what actually is being called checksum of the hash function. It's very often utilized in the communication field. So it looks pretty bad, stupid way, but it actually works pretty well. The procedure is this. Checksum method is first take all the digits and sum all of them, and second apply the modulo operation and the summation to the summation of the digits. For example, if we have this key and table size is 100, and we just add up every values here and modulo 100, and it's going to be 46. It's very stupid, but why people use these stupid ideas? Actually, this mid-scale values isn't it kind of brilliant? Actually, it's much brilliant than this digit analysis. But digit analysis is much often utilized than this mid-scale approach. Why is that? Yes, because this digit analysis, it only takes the plus. And this is pretty much low cost of the calculation. On the other hand, multiplication of the big values, it can take a huge time. Because of that, it might have a high cost in calculating index values. And in the program, every time we need some kind of index-based access. And if we take so much time in every call of the index, then that's a problem, right? So that we want to have a hash function with low calculation cost, and digit analysis based hash function is the best.